Welcome back to Introduction to Computational Fluid Dynamics, CFD. I'm Professor Steve Miller. Today we'll be talking about a code overview specifically for SU2. In our previous class, we did a crash course in computational fluid dynamics, and we looked at everything from the equations of motion, their discretization, and then the three major steps of CFD, the pre-processing phase, which involves the geometry and creating the computational domain and setting boundary conditions, and then running the solver, which involves, of course, the solution of the discretized equations. Then we looked at convergence and stability of the simulation. Finally, we took the solution, given if it solved correctly, found convergence, and it was stable. We then looked at the results through a visualization software. We inspect the solution, and of course we graph the results, and we make decisions based on those results. It's a general process of CFD. We had a quick crash course to show you all the major elements. In this class, we'll have a general overview of the particular software we're using in this class and how it's used in CFD. We'll look at installation and setup. We'll also discuss this more in detail in our one-on-one sessions. In particular, in this class, we'll be looking at the GMSH software, which is a grid generation tool, just for installation. We'll look at the SU2 CFD code, which is going to be used as our solver, and we'll look at the Paraview software, which is, of course, our visualization software. We'll mainly spend our time focusing on installation and running the most basic SU2 case and looking at its results with Paraview. Grid generation is much more complicated and not suited for an introductory class. First, we need to install our software. You can have Windows, Mac, OS X, or maybe the new ARM Macs when they come out in 2020 and beyond. There are versions of the software for Windows, Mac OS X, and Linux. They're all native, so you don't have to worry about something like virtualization or different like dual booting or anything. You can just install the native software. And I did a lot of this class on Mac OS X, and so that's what I'm most familiar with. But Windows will be very similar. In fact, where appropriate, I've tried to show the equivalent Windows commands. If you're running on Linux, you'll see that all the commands are basically exactly equivalent to Mac OS X. That's of course because Mac OS X is based on BSD, the Berkeley software distribution, and Linux is based on the same principles of Unix kernels. So they're both like inherited from the Unix ideas. Now, we try to mirror some of these installation files on our class website. If you can't find them there or you want the most up-to-date version, you'll have to go to the websites themselves. There's listed on the top of this page. The first is GMSH. That is our grid generation tool. You can simply go to this link here and you'll find installation instructions. We'll show you what the installation needs look like if you're successful. SU2 will be located at this particular link at the time of running this course, and of course I'll also have an updated link on the course website. Finally, we have Paraview. This link's unlikely to change, and that would represent, of course, our visualization software. We'll talk more about these in class and, of course, in this particular video. Now, the installation of GMSH and Paraview, that's your grid generation and visualization software, is going to be very straightforward, and it'll feel like installing any other program on your desktop or laptops. SU2, for some of you, will be very different. SU2, when you download it, will come as a set of binaries, that is executable, so you don't need to compile anything. That is, it's ready to run by, of course, your native operating system. On Windows, it's most likely to come as a zip file, and on Mac, it's most likely to come as a tar.g file. These are just both simply compression file formats. On any system, I suggest creating a folder or a directory and call it SU2. I located mine in Google Drive, and I'll point this out later in the class. That way it's automatically synced as I run small cases at least. You can really call this folder anything you want, but I suggest just calling it SU2. Create it in your home directory. Now, you'll extract your extraction or zip files or tar.gz file directly into the SU2 directory or folder you just created. This will create a whole file structure and tree with many subdirectories and appropriate files. So that's why it's appropriate not to just put it in like your home directory itself. You'll just create a mess. Now, you'll download also the tutorial database from the SU2 website or download it from our class website. I'll try and mirror it on the class website. So you'll note that you'll have in your SU2 folder another subfolder called tutorials, and you can extract those files into the tutorials directory. Now you should see the following directory structure after you repeat these commands. You download the software, you create a directory called SU2, and you extract SU2 and the tutorial database files by uncompressing them in the directory. You should now see a particular directory structure. You can see directory structures with particular commands on Mac OS X. OS X is essentially the operating system of Mac, via the command line. If you're in Windows, you can simply open up Explorer and look in that file directory to see it visually. You can also do this with the Finder on Mac. There's also, of course, equivalent tools on Linux. I'm assuming if you're running Linux, then you're an experienced user and you'll understand these commands, which are equivalent from Windows and OS X. Let's look at the actual file structure I've now created. Here's my command line as you would exactly see in Mac OS X. I've opened up the terminal and I've changed my directory to Google Drive /CFD/SU2. So on my own computer, I already have a folder named Google Drive. Within Google Drive, I have a folder which I created already for CFD because I have different CFD codes. And of course, I also placed my GMSH and Paraview installations and files in the CFD folder. That way they're all in one place. Within CFD, I have another directory called SU2. Now, my username is SAE Miller. My computer name is Ophelia, named after, of course, the Shakespearean character. And bonus points to those who can identify what play she's from. Nonetheless, the little tilde just means it's shorthand for my home directory. So this means my username on the computer Ophelia, in my home directory, in the directory Google Drive, in the directory CFD, in the directory SU2. So I can go into this directory with the cd commands on Windows in the terminal or Mac on the terminal, and I can type ls. ls stands for list, and I use the option -lsah. This command, ls-lsah, will simply show me in a human-readable list format the subdirectories in this folder. You can see here it is its read, write, execute characteristics. Let's not worry about that for now. It has my username. I'm in the group staff, and it shows a relative size of these folders, not the data in the folders, and the date which they were created, April 12th, at this particular timestamp. And there's the name of the two folders. The first one's bin, and the second one's tutorials. Now, many people don't have the tree command on their laptops in Mac OS X. And you can see all these file structures easily just by using change directory commands and listing or looking at the directories. Or you can just do all this within a file explorer. Either way, the purpose of this is to make sure that you've extracted your directories correctly. In the same folder SU2, I can run the tree command on OS X. This is going to show me nothing but my directory tree. That is the layout of my directories and subdirectories from the SU2 folder, which I've already created. You'll see, most importantly, there's a subdirectory in SU2. And remember, you should see this with your visual file explorers or finders in Mac and Windows. A directory called bin under SU2. In bin is where my executable files are. In almost all Linux, BSD, Unix machines, there's directories called bin. Bin contains executables. Under bin, there's additional subfolders. That's the main directory where SU2 is really installed. But we won't run it from the installation directory. That would be silly, because of course it would create a mess of all our files. Part of the reason I'm telling you all this is so that you can structure your directories correctly and create many cases without causing additional problems of files merging or overwriting each other for additional cases. You'll also have a directory called tutorials. So when you extract SU2, you should have a single directory in general called bin at the time of this video, and a single directory if you extract tutorials in the SU2 folder called tutorials, of course. And it'll contain many different cases, divided into compressible flow, design, incompressible flow, multiphysics, and structural mechanics. Now, they might have removed or added more of these tutorials, but each one of these subdirectories is its own particular CFD case, which contains a grid file and perhaps a solution file and a script file for SU2, which we'll talk about in a second. For example, if I go into tutorials, compressible flow, and go into, say, laminar flat plate, I will have a CFD simulation that is ready to run for a flow over a laminar flat plate. It's that simple. And so play around now, pause the video, and look at your directory structure that you've, of course, just extracted. As I mentioned, I really want to emphasize the bin directory In the SU2 folder contains a single executable in it. Well, there's many executables and subdirectories and Python files, but one is called SU2 CFD. This is the executable of the SU2 program. It represents the solver and, of course, the program, the executable code, which will run our CFD cases. It represents the solver step of CFD. It does not represent grid generation or, of course, visualization. Now, SU2 in itself does not have a graphical user interface. When the code runs, it will look for an input file that consists mainly of the computational grid and a script file, which is just a text file which tells it what to do. You'll see that many advanced research solvers and even some production solvers and industry solvers use this format. And of course, it is designed in a way that is very familiar with the world-famous NASA Fun3D CFD code, which I'm a major proponent of. Let's look now at the full files and folders in the particular bin directory. So now I've changed my directory to my username at my computer in my home directory under my Google Drive, in my directory called CFD, in the directory which I created called SU2, and I CD'd into the bin folder. I now run the same command, ls-lsah, and you can read about these command lines if you're on OS X or Linux by typing man, M-A-N, space ls. And I'll show you all the command lines. Nonetheless, this will be a list format in human readable format. And in the rightmost column, I'm seeing all the files. Now, .py files are Python files. It's a scripting language, essentially, here. And we have a bunch of executable codes. You'll see one in particular called SU2_CFD. So this line right here is the most important point. And we won't generally mess around with any of the other files in this class. But you should know when we run a CFD code, many of these types of script files and Python files are called, and so are the files in the subdirectories. We generally don't ever want to mess with the files in the bin folder unless we're creating our own CFD code. And in this class, we're not modifying directly or changing the SU2 CFD code. We're simply installing it and verifying it's installed. So make note of this file location, SU2/bin/SU2_CFD. Some major other points about the CFD simulation. Remember, SU2 CFD is the key CFD solver in itself in this class. There are also files and subdirectories, which I've already mentioned. And you can go at the time of writing in this class, this particular link to see the current manual of the SU2 code. I'll have an updated and current link in the class website, but you can also go to this website and find yourself or simply use Google. Your choice. Once you go there, I recommend you bookmark it because you'll probably reference it a lot throughout the course. At this point, I'm going to assume that you've used and download Paraview, GMSH, and SU2. SU2 is a little bit more complicated to install, but you'll see how easy it is when you do it. You simply download it, uncompress it into a folder called SU2, and you're done. And you can look at the files to confirm that it's installed. We'll also run a case in this class just to make sure it's working correctly and set up. We also want to launch GMSH and Paraview just to make sure that they're installed correctly. So if you download and went through the graphical user interface, which is like any other program for GMSH or Windows or OS X or Linux, you should be able to launch GMSH. When you launch GMSH for the first time, you should see a particular graphic user interface come up like this. You can see this is laid out by a very simplistic CAD program. Here's the window on the right. If you launch GMSH, you should see a window like this. And I've launched version 4, 5, 6. You might have a later version, and that's fine. You should see this like relatively bluish white window here on the right. That's where your CAD models and meshes will form when you're using the program. In the upper left, you'll see a drop-down menu with these little triangles. You can, of course, click the little triangles to expand them. They're expandable lists. And the whole program is divided into the geometry portion, that is looking at CAD files and creating simplified geometry like spheres or cylinders and simple Boolean operations. And you can specify, of course, boundary conditions and what parts of the domain are fluid. And we'll talk more about this later. We'll also look at the meshing algorithm. So once you create the geometry, you'll create, of course, a mesh from that particular geometry. That's where all the mesh operations are. Solver is where if you want to run a FEM solver directly from GMSH. We generally will never use the solver options. We'll be restricted to geometry and mesh. That's where we create our geometries, etc. Don't be afraid to right-click in the software or simply double-click. A lot of options will come up when you do, and it's fun to experiment. That's really the only way you can truly learn a piece of software. But we'll be focusing on the fundamentals of grid generation creation and boundary condition specification within this program. In the File menu, which isn't shown on this Mac OS X window, you'll be able to choose File and, of course, Export. And you'll be able to directly export grid and boundary condition information directly into SU2. How cool is that? In our homework set on grid generation, we'll look more at this in detail. You can close GMSH now, and now we'll confirm that you've installed Paraview correctly. After you've installed Paraview, launch it. And you will see a window that comes like this. It's very much like any other piece of CAD software, except this is designed specifically by a consortium of universities and the United States government to visualize results from large-scale simulations like CFD. A lot of these icons will be familiar to you if you know anything about CAD software or anything in the past. It works exactly the same. We have a visualization window where, of course, we create plots of all different kinds. We have a pipeline browser where we can load in files and create operations on them to see different types of data, like extracting data, calculating different quantities, visualizing line plots, contour plots, etc. And we'll look at a little example of that in this class just to get you a flavor of it. And we'll have more in-depth homework on visualization later in the class, which of course uses this Paraview software at the time we're running this video. Up near top, you see all the typical operations. You have open and saving. You have all kinds of visual orientation of your window down here. You have operations on the data in here. And in the pipeline browser, don't ever be afraid to left-click to select things and right-click for options. You can pretty much right-click on anything in your browser. Once you load a file, it'll have certain options to perform operations. Also, when you open a file, which appears in this window, another little window will appear down here, which has properties that you can directly edit and, of course, apply them. One trick for this software is this little button up here where my cursor is. This means it'll automatically apply whatever you do. If you keep this checked or highlighted when you run Paraview, every time you make a change, it will happen instantaneously in the window. If you have this unchecked, you can make a bunch of changes to your visualization and they won't take effect until you hit this button essentially, or apply. So it's very important to remember that, and that tricks a lot of students. So it's a little tip right now already in the class. Now we're going to assume that your software is fully installed. You have a grid generation package, a solver, SU2, and Paraview. We are going to now focus on executing the SU2 CFD code to see what happens. Now, we're going to use one of the pre-made tutorials to do this because we know it's ready-made and ready to execute without any problems. So we won't interfere or change any of the files yet. So we'll look at a particular tutorial called the Quick Start tutorial. It's named that obviously for the reason that it's made to get you quickly started running your CFD code. The object is we're going to see if our CFD code is installed and working correctly. And also I've tried to provide these files, of course, on the class website and in accompanying homework folders. You'll see that you're going to look at this particular case or a variant of it for one of your homework problems. Now, there's a part of the program and tutorials called adjoint approaches. We will not look at the adjoint approach. So if you get to the adjoint part of the tutorial, which you can look at and try and run yourself, go step by step as you look at this video too, if you wish, you'll come to an adjoint portion. Just stop. You're not going to need that right now. And that could be a future subject that we talk about later, but it's much too advanced right now. We just want to see if our solver runs for a new CFD user. Now, in my notes and in class notes, you'll also see that there's additional screenshots showing the particular process, which comes with the homework set for this case. So we ask you to go to the SU2 directory. So you'll CD to the SU2 directory. And for every case or every simulation we run, we will create a new subdirectory in SU2. We will. Never reuse a subdirectory. Always create a new subdirectory for every case you're studying. This way, they won't be mixed up. Some students make the big mistake of running all their CFD or parts of their simulations, like 5 or 6 simulations in the same directory. And they, of course, overwrite files and it gets all mixed up and they're confused. This is why for every simulation, every unique case, create one directory and put your files in that directory and run it from that directory. This way it's guaranteed that they're never mixed up. Don't make this mistake. It'll just create a major headache later. We'll call our directory under SU2 Quick Start. I'll show you these commands on, of course, OS X. You can run the similar commands on Windows command line or simply use the Finder Explorers to do them yourself. Here's the first command. I am in my SU2 directory. I've CD'd or changed my directories into it. So you see here's my username, computer, my directories, Google Drive, CFD, SU2. In SU2, I'm going to type mkdir, that's make directory, space quick start. So now, remember, I initially in this simulation had two directories, the tutorials and bin, where the CFD executable is. Now I've made a directory called quick start. And I can call it whatever I want. If I'm running NACA LL12 airfoil at Mach 20, I can call my directory that. NACA, say 0012 M20. Here now I've pressed entered, and my next line comes up, and I type in ls and enter. ls, remember, means list. It will list the directories in the folder SU2. That's listing the directories where I'm from. Now that I've made that new directory called Quick Start, it appears in the list. I have directories bin, Quick Start, and tutorial. Yes, that is great. Now, I would like to move into the directory Quick Start. Change directory is CD. I type in CD Quick Start. You'll see that my command line now says Google Drive CFD SU2 / Quick Start. What I've done is I was in the SU2 folder, I created a directory, I confirmed that it exists, and I moved into it. And so now I'm operating my terminal in the Quick Start directory. Now you'll see there are no files in this directory because I just created it. So I could type in ls, and of course it would return nothing because there's no files. Now I want to run my CFD case in this directory. I need to move in some input files for the SU2 code to work on. The SU2 code will require two major files. One is the configuration file. The second is the grid and boundary condition file, which is combined in SU2. So from the tutorials directory, you'll have to go in with File Explorer or CDN to the tutorial files and go into the Quick Start tutorial or the Invisted NACA 0012 tutorial and copy the file called inv_naca0012.cfg and copy the second file, mesh NACA 0012_inv.su2, into the directory which we just created called Quick Start. If you have trouble copying directories and navigating folders, now's a good time to go online and look up a basic tutorial. There's many people online with videos and quick tutorials who can explain this better than I can. And if you have really a lot of trouble, ask another student, and if that fails, of course, come to me. Now, we have a new subdirectory called Quick Start in SU2 with two files in it, the configuration or CFG file and the grid file called SU2. The CFG file is a text file. You can edit it, and it tells the solver what to do. The SU2 file is a grid file. It contains the geometry, that is the grid points, and the connectivity of the domain, and what are the boundary conditions. We'll talk about these files more in depth in the homework and in this class. These files represent the input of the CFD solver. Essentially, in practice, all CFD solvers work this way, except some advanced solvers will hide this information from you, especially commercial solvers. They have grid files. They have configuration files that are stored in memory or on disk, and they're read by their executable. Now list the contents of our new directory just to make sure we have it set up correctly. So we've copied our configuration and SU2 file in it, and now we can type ls-lsah in the Quick Start directory, shown here, and we'll get a number of listings. Don't worry about the dot and double dot. You'll see that there's two rows, one which shows, of course, the configuration file and one for the SU2 grid file. Now, you might be wondering what's missing. We're missing the executable file. It is bad practice to copy the whole CFD executable from its bin directory into its directory where the case files are. The case files are the grid and, of course, configuration file in this case. Instead of copying it, we would create a symbolic link, which is more ideal to the present directory. And I'll show you how to do it on OS X. In Windows, you can navigate to the bin directory, right-click on it, and create a symbolic link. You can then move the symbolic link or quick start link to, of course, the quick start directory. On Mac, it's much easier, and you'll see in the quick start directory, we only need to type this command, which I've shown at the top of the page. I would write ln-s. Now, ln is the command which creates, of course, like a symbolic link on OS X. And from the quick start directory, mind you, I'm still in the quick start directory. -s means it's essentially a symbolic link. And then I say, what is the file I'm creating the symbolic link from? Well, I would write /bin/SU2 CFD. And then I would write where the file will be located. I put a space and a dot. Look at this command very carefully. It's easy to mess up. So this command has a single structure, ln, which is the command to create the symbolic link with the symbolic link flag, -s, space, the file source, space, the file destination. The destination is just written with a single dot, meaning it's the present directory. Now, the source means that we're going down a directory, the dot, see we're in quick start, so we go down to the SU2 directory, and then /bin, which goes up to the bin directory if you remember the file structure, / the file name, capital SU2_CFD. Capitalization is important. And it's a good practice to have because one day you might be using a case-sensitive file system. You could be, depending on the type of installation of OS X you made. Or you might be running on Linux or BSD. The dot means it puts the symbolic link in the present directory. Anyway, try out this command exactly as you've seen it. You're in the quick start directory, you type ln space /bin /SU2_CFD space dot. Enter. And if it worked correctly, you can then type in a new list command from the same directory. Type in ls-lsah, and you'll get a file listing. You'll see our configuration and, of course, grid file are still there from the previous step. But a new file has appeared. And this file is called SU2_CFD, which is the name of the executable with an arrow, which is represented by a dash and an open bracket, with its path to the executable. And it's /bin/SU2CFD. So every time you create a new CFD case, you'll have to do this process. You can always just copy the symbolic link. You don't have to redo the command. But you'll copy the symbolic link. Do not copy the executable because the executable will look for dependencies in some directories from the bin directory. And your code will fail and you won't know why. Now, we have everything set up for the CFD code to run. We have a symbolic link to the executable in its own subdirectory. We have a configuration file and we have a directory file. That's great. Let's now examine the configuration file with your favorite text editor. On Windows, you can just simply use Notepad or something. That's fine. If you're on, say, Linux or Unix, you can use something like Emacs or Vim. And if you're on OS X, of course, you can just use the text editor application. All those are fine. Try not to use like Word or some other word processing programs. They'll corrupt the configuration file when you save it. And also won't look weird on the screen because it won't be formatted correctly with a strange font. I recommend personally to use Vim or VI. It's a famous text editing program. It's a little bit complicated, but once you get used to it, it'll be faster than anything else. For new users just starting out, who aren't familiar with like Unix or Linux or OS X and these types of commands, if this is all new to you, just use Windows Notepad and you can open the file and save it without having any problems. And you'll have a graphic user interface. A lot of students like that, but it'll never be as fast as say like a VI or Emacs program. Now, to edit the file, I'm going to use a VI in my examples, but you can use Notepad and stuff. Basically, I want to open the file inv_NACA0012.cfg. That's what I've done. So on the command line, I simply type in VI or VIM and the file name, and I push enter, and it'll come up in my screen. And of course, if you've never done this before, you'll have a lot of trouble even executing or saving the program because they all use like specialized command keys. So decide now if you want to learn a rigorous way with VI, which will help you work on supercomputers in the future if you want to stay in this field, or if you want to stick with Notepad or something like that. And that's fine either way. You can always transition later. When I hit enter, I'll see the, of course, context of the configuration file. Let's talk about its basic structure now. We're going to look at the configuration file. When the CFD code runs, the first thing it does is read the configuration file, and that tells what the CFD solver to do. It'll then read the grid file, which is specified in the configuration file. How cool is that? Let's look at this configuration file. This is the beginning of it. Note I've written truncated near the bottom because the configuration file is many lines long, because good CFD solvers have lots of options and bells and whistles for you to play with. Now, in SU2, the first thing to note is the percent sign. The percent sign means a comment, just like some languages like MATLAB or other programming languages. The first part of the file is usually the header, and it just talks about what the case is. It says the SU2 version, the date it was originally created, the institution and author, this person, Economon, he resides at Stanford in 2014 when he created this file. There's a case description. So these are all just comments. The solver itself will skip the comments with percent. It'll only read in non-percent lines. And of course, it says it's an SU2 file. So you could actually delete all this. You could edit it to make it your own if you create your own. Well, it wouldn't be very polite not to attribute the file to its original author. That'd be sort of like academic dishonesty. But nonetheless, when you create your own, you can create your own header files. It's a good practice. That way you don't lose track of what the configuration files do. Make many comments, just like you make many comments in a programming languages. Think of this as like a scripting language for CFD, and you can make many comments as you wish, except it's much more restrictive. Now going down, there's percent signs and shows that these are comments. So the first thing we do is tell the solver what set of equations we're solving. We say solver equals, see there's no percent sign, so this is like something the solver is going to read and interpret. We say the solver is equal to Euler. This means we'll be solving the Euler equations. We can also say solve the Navier-Stokes equations. To do that, we would change Euler to Navier-Stokes. So you can see there's a whole classification of equations we can solve. In fact, there's even more at the time of this class. This was in 2014. Believe me, in 6 years at the time of this video, 2020, many additional equations and solver parameters have been added. Nonetheless, this case file still works. Then, of course, we dictate if it's a direct or adjoint calculation. In this class, we'll predominantly be using direct. So we say math_problem equals direct. So all this is already programmed for you. It's ready to run, and it will work. But, of course, we're just looking at it to understand. Here's a restart solution. If we already have run the solution or CFD for a while and we want to restart the code later, we could turn this to yes. By saying restart_sol equals no, it shows that we're starting the CFD solver for the first time. So anyway, you can go down the list and see all kinds of different comments which describe the commands and what they're set to. You can get an idea of the power and what you can do simply by changing simple parameters in the solver. For example, we can completely change the equations that we're solving in the CFD solver with the same grid and boundary conditions with just a single command of solver equals Euler to Navier-Stokes. It's that simple. So anyway, we are now really ready to run the solver because we have a directory. We have in that directory a grid file configuration file, which we looked at, and we understand what it does now, if we went through the whole file, of course, and we'll look at that later, especially in our homeworks. And then, of course, we have our symbolic link. So we're ready to execute the code. Let's try that. When you execute the code, it will generally be shown on screen. So if I just type SU2 CFD, the symbolic link executable file, space the configuration file, inv.naca0012.cfg, and hit enter, the CFD code will run, and it'll put a lot of information on the screen. We're going to talk about what that means in a few minutes, just as a broad overview. Now, I personally like, when I run the code, to have it go to the screen and to a file. That way I can see it run on the screen and I have a recording in a separate file when the simulation's done. Or if it crashes, I can send that file to, say, my friend to help me figure it out. Now, generally, output files will be shown on the screen. For now, just send it to the screen. Pipe it to the screen. That's fine. And when you run successfully or unsuccessfully, the code that is, it could crash or fail or diverge, blow up, or may just run out of iterations. It will place, or if it finishes successfully, it will just place many files in that subdirectory. And these will be, of course, the solution files and the residual files, which we'll look at a bit more in this class. Now, a command I prefer to use is shown right here. I put that as my username, my computer, and the directory I'm running, quick start, and I've typed in on OS X, this won't work on Windows, SU2 underscore CFD space my configuration file name, inv underscore NACA0012.cfg. Remember, I can name my configuration file anything I want. I could call it, say, chicken.cfd. So I could write SU2 CFD chicken.cfg. And it'll read that file. But it's better to always name it something that, makes sense. Now, this is the required part of the command to run and execute the code. And some cases will take a long time, so be patient. And you'll be running this code a lot of times during the semester, so it's good to get used to this now, of course. We'll have SU2 CFD space configuration file. Hit enter, it'll run. Alternatively, if you're like me and you want to send the output to the screen and a file, the file I send the output to from the screen is called output.txt. It's a text file too. I can read it with a text editor on Windows or Linux, etc. The command will be 2 bracket and 1 space and space t space output.txt. You can try and type this command yourself, and you'll see that when your code ends and as it runs, you'll have whatever appears on the screen also be in the output file. If you have trouble with this, don't worry about it for now, and just run SU2 CFD with the configuration file and truncate the rest of the command. But if you get used to that, you'll be very happy if you can figure it out. Now, on your terminal window, which you're running this from, you can't just double-click SU2 CFD from your file explorer. You have to run it in the terminal with this command. You will see the following output if the code ran correctly. Let's look at the output of the SU2 CFD code as it runs on the screen. Here, I've run the command without my extra information to pipe it to a file. I've executed SU2 CFD inv underscore NACA0012.cfg. So the first thing that appears whenever you run the solver. It's just the comments. This is the version of the solver of SU2. See, this is just printed for every time you run. It's talking about licensing information and copyright and the code and everything. And then basically, it's also mentioning it's free and open source. So you'll never have to pay. It'll always be free. No payment, and it's free as in money and free as in beer, as the famous computer scientist Richard Stallman would say, in that you can see the source code, you can modify the source code as long as you redistribute it freely using the same GNU Lesser Public license. So you can get the source code, you can edit the source code, you can recompile it, you can add in your own models, modifications, whatever you want, and you never have to pay for it. That's cool. And of course, it's created by a consortium of universities and industry. So the first line, and there's many lines, we'll just say it's parsing the particular file for zone 0. Don't worry about that. And now it prints out, this is all printing to your screen as it runs. It's going to solve the compressible Euler equations, the global Mach number, which we'll talk more about later. We'll talk about a lot of these things in this class. You understand them is 0.8. So the incoming flow is a Mach number of 0.8. The angle of attack to the airfoil is 1.25 degrees. There's no side slip angle. There will not be a restart solution. The solution is dimensional using SI units, and it has reference links. So read through this yourself and you can get some ideas. There's a surface in the grid file called airfoil, and that's where we'll be evaluating lift and drag. And the input mesh file, which is specified in the configuration file if you inspected it, is called mesh NACA0012 INVSU2. This file is specified in the configuration file, and it's telling the CFD solver to read it. So in the configuration file, you should have this command within it for the grid file. If the code cannot find, if SU2 CFD cannot find this file, it'll crash and stop because you've told the code to read the file, but it's missing. That's why it's so important to verify all the files are present in the run directory. Then, of course, we talk about the numerical integration technique. It's going to use the so-called Jameson-Schmidt-Turkle scheme. We'll talk about these numerical schemes later in the class. So this is the type of discretization and solver it's using. Then we talk about the type of time integration scheme it's using to solve the equations. So this is all derived from the input file. A CFL ramping technique is used. We'll talk about that in class. A multi-grid technique is used. We won't be talking about that. It's a little bit too advanced, and we'll generally not use multi-grid techniques in the class, but it's enabled for this case. A CFL number is defined 10. That's basically like the speed limit of CFD, and we'll define that mathematically and talk more about why that's important in this class. Then we talk about convergence criteria. This is basically the criteria for when the solver stops. Now, there's a few important things here, like the maximum number of solver subiterations are for 250. That's a rather large number. We'll start looking for convergence after 10 iterations. This is the output information. This is what the solver will be putting out into files into the screen. It will, for example, be writing solution files every 250 iterations. So the solver will cycle, and every cycle is an iteration towards a solution. Every 250 iterations, it's going to write a solution file which contains the densities, velocities, pressures, temperatures, etc. on the grid points. It'll also be writing a convergence history to another file every iteration, and it'll be writing to the screen, which is what we're looking at right now, information every iteration. It's going to put this information also in a CSV format, that's comma separated value format, which can be read by Excel or a text editor. And that file name will be history. It'll break down the forces on the airfoil in a forces_breakdown.dat file, which is also a text file of course, the forces on the airfoil. And the file names will be called surface flow for volume, so there'll be a volumetric flow solution file at the end called flow.dat, and we'll look at that in this class. And there'll be a restart file name, so if we restart the solution from a later time, it'll be restarted from this restart_flow.dat file. Note all these file names and iteration counts and all this information is specified in the configuration file as a single file. That's why it's important to keep your configuration files separate from one another, and when you start a new simulation, which is similar to a previous one, you can simply copy and rename the configuration file to a new subdirectory and edit it. These are the specification of the values of the solution on the boundaries of the domain. For this case, there's two. This is a table. The first column is the type of boundary condition, and the second column is the name where it's enforced. The first boundary condition in the first row is an Euler wall. That means it's a flow condition where the velocity is tangent to the wall and it can slip. So it's a slip wall boundary condition. We are not enforcing the so-called no-slip boundary condition, which means the velocity is zero at the wall. We're specifying it at the airfoil surface. Then we have a far-field boundary condition. This specifies the Mach numbers, pressures, temperatures, and velocities far away from the airfoil. For example, the Mach number at the far-field boundary condition will be 0.8, which was specified, of course, way up here at the beginning of the simulation where my cursor is. And of course, that's specified at the far-field marker. The markers have names. The CFD code says all the boundaries that have the marker far-field will be assigned the far-field condition. In the grid generation code, which comes before the solver, we specify the locations where these boundary conditions are and assign them names. You'll see that in the grid generation part of the class and the solver part of the class, we're using the same names. For example, in the grid generation code, we'll call it the airfoil surface airfoil. And in the solver configuration file, we'll call it airfoil. It's that simple. Here's some information about what will be written to the screen. So for example, we'll have wall time, root mean squares of densities, we'll have lift and drag. You can specify whatever you want written to the screen as it runs to track, of course, the history. Now the code has read everything in the input file, and now it's going to start processing the computational grid. Let's read through the geometry processing algorithm. The SU2 code found that it's a two-dimensional problem. There's 5,233 grid points. There's 10,216 volume elements. There's 2 surface markers, which correspond to airfoil and far field up here. There's 200 boundary elements on the airfoil surface and 50 boundary elements in the far field. The domain consists of 10,216 triangles. It's in 2D, so we can't have tetrahedrals. We could have, say, like little squares or something, or hexes, or rectangles or something like this, but we cannot have anything but 2D elements. And in this grid, it's just only triangles. So the total number of triangles formed is 10,216. You'll notice there's no other element type, so it's no coincidence that there's also 10,216 volume elements. They're equal. That's good. Then it goes through and looks at connectivity and makes some checks to make sure the grid is suitable for a CFD run. Let's keep down. You're welcome to read these quickly if you want, and we'll get down to quality checks. Now, in our grid generation software can often run these quality checks too. SU2 is also looking at the quality of the grid, and it's telling you, say, orthogonal angles, aspect ratios, cells, etc. We'll talk about what these mean and their importance later in the class in our grid generation module. It also uses multi-grid. Let's not worry about that now, but it's a convergence acceleration technique. It is not required that we use multi-grid. Now, it tells us more geometric information. This can be easily calculated from the grid. Now we get down to the solver preprocessor phase. It detected that we're running an invested flow because we selected the Euler equations. We're computing the density based on the so-called free stream value and the temperature and pressure based using the ideal gas law. This is for, of course, the boundary conditions. It's just automatically telling this. It's nothing we have to specify, remember. Now it's telling us what models we're using. For a viscosity model and connectivity and fluid model, we're just using standard air. Simple. We can specify our own values, but right now we're just using the standard air model. So it's just like air in our room. We're looking at some fluid properties, and these are familiar to you from your classes. We have gas constants R, which have units of Newton meters per kilogram Kelvin, and they have, of course, the units 287.058. We have a ratio of specific heats of 1.4. Remember that's Cp over Cv from your thermodynamics class. And then we have our free stream values. In these particular columns, they're saying the static pressure, density, temperature, energy, velocities, and velocity magnitude. This is the properties of the gas at the outer boundary of the domain, the far field condition. This is corresponds to the Mach number we specified and the standard air models. So for example, the atmospheric properties far away from the airfoil is 101,325 pascals. That's basically the standard atmospheric quantity. And so is density and temperature, 273.15 Kelvin. This solver can also run in English units if you live in the Dark Ages, or SI units by default if you live in a contemporary, modern, civilized age. Now we can also look at Mach number. The Mach number, of course, is listed last from this table. So the solver initializes and defines Jacobian metrics for multi-grid, not too important right now. And then after all this stuff, after reading the files, checking the grid statistics, looking at the solver, and outputting all this information to prove to the user that the solver has read the configuration file successfully, it finally starts the solving step, which is great. So we're beginning the solver right now at this particular step, finally. So the simulation will run using a single zone. That means we have one fluid volume. And for every iteration, we will have a value of 0, 1, 2, 3, 4, all the way up to the last iteration. So the iteration, remember, is like the cycle of the solver. It is iterating towards a steady solution of the simulation. Each row represents statistics per one iteration. Each column represents something, a particular statistic. The first column is the iteration number. It's called inner iteration. Don't worry about that for now. We'll talk about the difference between inner and outer iterations later. But right now, for iteration 0, it gives us a particular time. Don't worry about the time column either. It says also the root mean square of the density. This is the residual. It is the error in the simulation. Our objective is as the simulation runs, this value decreases. We will talk more and have a whole class about residuals and convergence. The objective right now is the iteration increases, the residual goes to 0 or a very small value. It also reports the solver as a bonus, because we specified it in the configuration file, the coefficient of lift and drag for this airfoil at this Mach number and angle of attack. How cool is that? Now, as you see, as the iteration increases, the steady flow will converge to, of course, the correct solution, we hope. And there'll be strategies to see that. So let's watch our code run, and you'll watch the iteration count increase. It goes down, and I've truncated it. And at iteration 169, on my current compiled version for this particular file, my code has essentially converged, meaning you see here's this column is density, root mean square of density residual, and it's gone down to -8. It has satisfied my convergence criteria, which I specified in the configuration file. You'll see the coefficient on the left and drag end up being 0.326931 and 0.21435. So I could say that because my RMS of density residual has gone down to the -8th power, that my convergence criteria is satisfied. If you look in the configuration file for this case, you'll see a convergence criteria. It's set to -8. Notice we achieved a value -8.003. -8.003 is less than -8. So I'm converged, I'm done. I stop my solver at iteration 169. It's simply an if statement in the solver. Every iteration calculates the error in the solution, and if the error is less than some value, I stop. And I say, yeah, I'm converged, that's fine. You'll see, at these last iterations, my coefficient of lift and drag were not changing much. In fact, they've kind of converged to a single value. Up in the beginning, they changed a lot per iteration. So look at the early iterations, 0 through 4, and look how coefficient of lift and drag were changing so much. At the end of the iteration, they converge to a single value. That's a good thing to look. As your solver progresses, your residual errors and your forces, if it's a steady simulation, should converge to single values. I could then say the coefficient of lift and coefficient of drag at Mach 0.8 at this angle of attack are these two values, if we're solving, of course, with the Euler equations that are steady in 2 dimensions. That's my major result from the solver, but I can also calculate and look at these quantities in more detail with the visualization process. But we're not done. The solver has to close out. After the solver says I'm exiting successfully or not successfully, which is another problem, we can then see what files it writes. The solver wrote a restart file called restartflow.dat. This appears in your run directory. So if you type ls, you should now see these particular files appear. If you restart your simulation, you can restart from iteration, say 169. You do not have to start from iteration 0. And so by having restart files, that's very valuable. To do that, I would go in my configuration file and change restart from no to yes. The simulation would then read the restart file and start from iteration 169. It's also written out a very important file called flow.vtk. Flow.vtk is a Paraview file which can be read by, of course, Paraview. It's a binary file, so it's written in, of course, something that's not human readable. It's written in the machine language, and it can be read directly by Paraview. We'll be using Paraview, which is visualization software, to look at that file next. Nonetheless, the solver does some cleanup. It's deleting extra little containers of files and things. And of course, it exits successfully. When you see this particular command, your solver is done running, and your command prompt returns. If you return and see a similar output, then congratulations, you've run your first CFD run using the SU2 solver, and you've executed the quick start tutorial. So let's examine the new files in the directory. The solver is done. Let's look at the output files. I can, once again in my quick start directory, type ls-lsah to see all the files in the directory. And you'll see I have the same symbolic link. You'll have the same configuration file and the same SU2 grid file. But you'll see we have many new files and they're fun to look at. That's half the fun of CFD. Now we're entering the visualization stage. We have the flow.vtk file. That's a binary file that can be read by Paraview or your visualization system. Your history file is your history of residuals, which we can examine to and prove convergence. We have an output.txt file. That will appear if you piped your screen output to a file, but it's not required. That's only for maybe advanced users who want to see and restore their screen output. So most of you will not appear. We have the restart file, which I've already discussed, and we have a surface flow.vtk file, which is another Paraview visualization file to only view the flow on the surface. But we can simply do that within the flow.vtk file. So surface flow.vtk is not that useful. It's there anyway in case we want to use it. You'll note these new files and start to remember what they do. Let's examine the new ones in more in depth. I'll let you read through this on your own, as I've made, of course, notes on these files which I just discussed. Now, the next step of CFD, we've essentially completed the first step, is to visualize the results. Let's do that now with a particular post-processing technique. We've now entered the post-processing technique. Let's see what we got with our flow.vtk file. Once again, start your visualization software, Paraview. Now, you can load, by saying file load or open, the flow.vtk file, which appeared in, of course, your quick start directory. So load that up. Alternatively, if you're on Mac OS X or Windows and you have the File Explorer up too, you can simply right-click the VTK file, click Open With, and paraview.app. This is the Windows screen, but the similar thing happens, of course, on Windows. Excuse me, this is the Mac screen shot, but the similar thing happens on Windows. So we can note the following screen once we execute the loading command. We'll have a visualization of Paraview that looks like this. Initially, we don't see anything. But you'll notice that now in the pipeline browser, and everything else looks the same, we have a little thing that says flow.vtk. That means we've successfully loaded the solver. Now to view the file itself, And these programs are designed to view very, very large files. That's why they're so careful and don't do too many things completely automatically, because, of course, they want to make sure to execute demand with the user's permission. We would click the little I, which is next to my cursor here. So you can see if you zoom in on your screen, look closely with the file open. So I select the file, so it's highlighted in purple, because I like purple on my screen. You might have a different color like blue. This means now we're visualizing the file. You might also have to click this little button up here to automatically apply every command. And that's okay. There'll also be an apply button which appears on the screen if you don't do that. So try that out. Click the little I, and we'll see what happens. Here, let's zoom into the little I. You can see there's a little I, and I left-click that I with flow.vtk highlighted. Great. Now, the next thing you should see is my data will appear in this large gray window. You can use your mouse wheel to zoom in or out. Try that out. And you can left, middle, or right-click buttons to pan, zoom, and rotate the display in three-dimensional view respectively. So in this window, if I'm using my mouse wheel, my left button, my middle button, or my right button on my mouse, so you might want to get an external mouse for this instead of your laptop trackpad, for instance, you can move around. And you're probably familiar with all this from your previous classes in CAD or something. If it's your first time using this, then take some time now to look at it so you can learn how to move around three-dimensional models. If you make a mistake and can't see the model anymore, you can use these buttons up top here to reset the views. Just click them and it'll reset the particular views. You can click these scaling buttons here to scale around the model and change the axis views. You can also rotate the view here. You can change, of course, the display, the axis down here, and you can rotate around by clicking and dragging with these buttons up here where my mouse is moving. So get used to those. Those are just for visualization in the gray box. Remember, you're always clicking and dragging and mouse wheeling for moving the model around in the gray area. That's easy. So at this point, hopefully, you've loaded up the VTK file, the flow.vtk file, which is the solution file written by the CFD code, and you've clicked the I and you can see it. If not, then there's some great visualization tutorials which will be linked from the class website to get you through this step. And of course, if you get stuck after that, please talk to me. Now, before we go on, I need to mention that Paraview is a very powerful data visualization program. It's developed by the United States government, so you know it's pretty serious, by our national labs and associated university consortiums. It is free to use and is open source forever. It works exactly like a CAD program, but its specific aim is only to visualize data of very, very large time-dependent data sets. For example, what if my data set was terabytes large, distributed all across many different computer systems? I could use this tool, of course, to examine the data. That's very powerful. And so by using this tool now and learning it for simple cases, you'll be able to execute it for very complicated CFD solutions later. You're not going to be able to visualize your data with a program like MATLAB. Once we've clicked the I, we can zoom closer to the airfoil with the mouse wheel and change the menu to Mach number via the pull-down menu. So if you look at the top of your screen, and I'm on Mac OS X, I see a little pull-down menu around here. One is for surface. Leave that as surface in the pull-down menu. That's what we're visualizing. But you'll see a pull-down menu that has something like different quantities in the flow simulation. They might be pressures or magnitude of velocities or other quantities, but we'll just select Mach number for now. So select Mach number. Make sure your eye's on, and you're always selected flow because we're operating on this particular file. We can always have multiple files or operations open. We're always operating on the one which is selected. So make sure that's selected. Make sure your eyeball's on, open, and then use that pull-down menu to select Mach number. Now in the right part of the screen, you will see contours of Mach number. You'll see a contour legend for Mach number from about 0 all the way to 1.4. The contour levels, of course, are displaying the Mach number around the NACA airfoil. The NACA airfoil is shown in gray. The flow moves from left to right. You can see we have a very, very high Mach number in red on the top and lower on the bottom. A very low Mach number near the front and back. This, of course, is an inviscid flow around the airfoil, a low angle of attack, with incoming Mach number about 0.8. You can see this is about 0.8 on the screen over here. It's relatively undisturbed flow. The flow comes in, it comes up, it goes around the top of the airfoil. The speed increases, the Mach number increases, and then it hits a barrier, and it decreases instantaneously almost and decodes downstream. This is actually a weak normal shock wave attached to the top of the airfoil. This is a transonic airfoil case, and we've just solved it with the CFD solver. That's very exciting. So some notes about what I just stated in writing. You're seeing contours of Mach number around the airfoil. See if you can view the computational grid now by enabling surface with edges. So if you go back to the screen, you'll see surface. Click surface and change it to surface with edges. You'll now be able to see after you hit apply, or if you have it automatically applying the visualization, surfaces, that is the grid points and grid lines, superimposed with Mach number. We, of course, can see changes in the whole flow field of Mach number or other quantities. We could change Mach number to, say, pressure, P. That's the static pressure, the internal stress of the fluid at any point in the fluid. Look at those contours, too. It's quite fun. Now let's examine something more quantitative, and the airfoil. Let's close Paraview and reopen it. Let's restart. And open now the surface_flow.vtk file. So instead of the flow.vtk file, we're opening surface_flow.vtk. And here I've shown a screenshot about apply changes automatically. So when you're learning, up here at the top of the screen, click this button and keep it highlighted. Single click turns it on, a second click turns it off. A highlighted button means it's on. And this way, when you click things and change parameters, you don't have to click reapply every time. This will automatically reapply the changes to Paraview. I've mentioned this before in this class, and now I'm showing it graphically. It's so important when learning. This way, you'll be like, oh, I made some changes and they're not doing anything. Why is that? Well, you're not applying the changes. This is important because, of course, some changes might take 20 or 30 minutes of the time of your computer to make the change. So you may not want to have that enabled when you're looking at data sets that are terabytes large. You might want to just have it completely checked for simple data sets like this, which only take a few seconds to change. Anyway, once you restart Paraview and load surface_flow.vtk, once again, click the I next to the name after highlighting the file name in the pipeline browser, which would appear right here, of course. We will try and add our first filter. Filters are operations on data. If we have a data and we filter it, it will be something else. A good analogy is, say I have light and I send the light through a filter. The light on the other side of the filter might be different. For example, say I have red and blue frequencies of light going to a filter. If my filter removes the red light, I'll only have blue light on the other side of the filter. It's the same thing with data. The data is the file that we read. In this case, it's, of course, surface_flow.vtk. We apply a filter, and we can try and extract or change the data with mathematical operations or extract certain parts of the data. We can put filters on filters. So just like we could put on different filters for light as it goes through a series of filters, we could put on different filters for data as it goes through a stream. The stream here is called the pipeline. So in the pipeline, we can add and right-click the flow.vtk file or surface_flow.vtk file, right-click, and there'll be a drop-down option called filters, and we select a filter to apply. Let's do that. Let's try and make a line plot from our surface data which we loaded. This is how it looks on my screen. So first make sure that you've loaded up Paraview, you've loaded the surface_flow.vtk file, and then you went up and clicked and grayed out this button, which means that you're automatically applying each operation. Now I make sure that my surface_flow.vtk file is highlighted in purple, and I make sure my eye is open. My next operation is to right-click the file in the pipeline browser, and I move my cursor down to add filter and a new menu forms, and I move it down to data analysis and a new menu forms, and I move it down to plot data, and I left-click plot data. Then a filter will be applied, and I'll show you what happens in a second. But let's just look at these menus. Right-clicking is your friend in Paraview. By right-clicking the particular files or filters which are created from them, I can execute all kinds of commands. I can hide and show data by enabling or showing the eyes for the files and all subsequent filters. Under Add Filter, there's a whole list of all kinds of common operations I can perform with Paraview. For example, there's chemistry operations that have, say, combustion data. There's interpolation commands if I want to find the value between particular grid points. I can find particular statistical quantities. I can find temporal quantities and data. Under data analysis are our most common operations. Plot data will make line plots from the data set. I can also extract data. I can plot data over times or lines. I can perform calculations. This is one that's extremely useful. For example, say I wanted to find vorticity. I could click calculator and a filter would be applied. My data in my pipeline would go through the calculator filter, and my filter would be defined by an equation for, of course, vorticity. I would have an equation of nabla cross u, and I would find the vector of vorticity. So I could define these calculator commands and a filter would appear, and I have the filter down there. Nonetheless, for now, just click plot data. Let's see what happens. Now, if you have the option to automatically apply commands enabled, you will see a new line plot appear on the right-hand side in the visualization window of Paraview. Unfortunately, there's too many lines to be meaningful, and we need to change that. You'll see in the lower left corner of your Paraview screen, if you have a fresh installation with default parameters, a properties box will appear. If you don't see the properties box, you can try and enable it through the pull-down menus on the top of Paraview, which aren't shown here in my screenshot from Mac OS X, but they'll appear at the top of the window for Windows. So in the lower left corner, there'll be a pull-down menu in the properties window. That pull-down menu will have, of course, properties. So go to Menu View, Properties. There's now properties associated with every file or every filter. By clicking the file or filter that newly appeared, we can see particular properties. So left click on the plot data, which appeared right here, and you'll see there's associated properties. These are properties that are associated with every file and filter, and the highlighted one is associated in the pipeline browser with the associated properties in the filter. So you should see some of the following properties in this page. We'll look at this in a sec, but let's just review. We will set that the index is for the x-axis is unchecked. We will change the X array name to X points, and we will set the series parameter to pressure coefficient. Let's see what happens in our windows. So you see now I have pipeline browser and a thing called properties. I clicked the newly created filter, and then I clicked properties. And so now I'm seeing the properties window associated with the plot data filter. I should see a window like this. Now, initially the right-hand side in this visualization window will look very different. It will look, of course, like a bunch of lines. In the attribute type, I want to have point data. That should be the default. Under x-axis properties, I want to uncheck use index for x-axis. If that's checked, it's using every grid point along the x-axis to plot the data. That doesn't make any sense because it's associated with the computational grid, not the physical coordinate system. I would change the X array name to X points. So these are the points, the X coordinates in the solution file where the data is stored. You can also change that to points Y, points Z, or any other quantity in the drop-down menu. It's essentially changing what the x-axis is in the plot. On the y-axis, you'll have the, of course, dependent variables. Here's the series parameters. These are the dependent variables on the y-axis. We want to uncheck everything. We could just click the minus sign to uncheck everything initially, and we could go down and click pressure coefficient. You could see I also could plot as an XY plot, say the density, energy, Mach number, points X, the pressure coefficient, or temperature. I basically perform these three simple operations in the pipeline browser, and I click apply, or if it's applied automatically with my highlighted cursor here on this button, and I'll have the visualization on the right. What we've done is plot the pressure coefficient on the surface of the airfoil from the surface data only with X coordinates, and I'll see two lines. Now, this is positive pressure coefficient, this is negative. Usually in aerospace engineering, we flip this. We flip it, but for now, we'll just look at it as it is plot natively in Paraview. The x-axis is the chord x over c from 0 to 1. That's the chord of the airfoil, x over c. The y-axis is pressure coefficient because it's highlighted. You can also plot temperature if you wish. We have two lines. This one is, of course, the upper surface of the airfoil. How do I know that? Because that's a shock wave. The lower one, of course, is the suction side of the airfoil. Look at these lines and plots of pressure coefficient and compare it to the visualization of the surface in this plot. You'll see here's the shock wave on the pressure coefficient on the top of the airfoil. So we've now calculated the pressure coefficient on the top and bottom of the airfoil with, of course, Paraview. We can then take this plot and make a screenshot of it, or we can go to File, Export, and create a PDF or EPS file, which will give us a vector graphic. I suggest getting into the habit of making vector graphics. You also notice it's automatically made a legend called pressure coefficient. This is a bit messy. You have the ability with the property windows to add in legends, to change the number of tick marks and everything on the X and Y axis, add another x-axis legend, etc., or change the pressure coefficient to maybe like C sub P, which would be nicer. You can also change the colors of these lines and change your line styles, all with the property windows to make something that looks publication quality graphic. But for now, looking at the solution, you're okay. We'll look more at these types of issues in the visualization system. And we've posted a number of YouTube tutorials, which I strongly urge you to go through on visualization software like Paraview is extremely popular, and there's many tutorials online, both written and on YouTube, that you can watch. I cannot make better tutorials than those who've used this software for years. I encourage you to look at some of your own tutorials for Paraview. I've posted 5 or 6 excellent tutorials focused on like CFD visualization and results on our class website. I really recommend watching them, and that way you can become a Paraview expert. They'll only take you maybe a couple hours to go through at most. As I mentioned, you'll see 2 lines, and these represent the pressure coefficients. I've mentioned the shock already, so my question is a little bit antiquated now, but you can see, of course, the normal weak shock on the top of the airfoil. You should now play with the other properties in the filtering window here. Try and plot, say, temperature, density, or Mach number on the airfoil surface. You might ask, why is Mach number non-zero on the airfoil surface? Of course, in reality, the flow will be 0 at the airfoil surface because of the no-slip condition. But remember, our boundary condition was a slip condition Euler, which we specified in the configuration file. We could easily rerun the code with a no-slip condition and get a more accurate solution. You can also add labels for x over c and c sub p on the x and y axes respectively. And if you're familiar with the famous LaTeX language, which is used for typesetting documents for journal articles or research articles, etc., you can use that kind of syntax. I'll talk a little bit about it in class. If you're curious, ask me about it. You can then, of course, make screenshots to make the files and paste them in Word documents if you're making a report, or better yet, a LaTeX document if you're preferring something more professional. And of course, you can write them as EPS or vector graphics through the system file commands. I recommend making vector graphics for line plots and not, sloppy JPEGs, which have lossy format for plotting. Anyway, try on your own creating a Mach number versus x over c plot or any other variables you're interested in. Let's now turn our attention to examining lift and drag. Now, we originally ran our solver with Mach number 0.8, and we found the coefficient of lift directly from the solver. Remember, when the solver ended, it converged and it gave us a coefficient of lift as a value. How does the coefficient of lift change as we change the Mach number of the airfoil, the global Mach number? Now, before we ran it at 0.8, let's run our airfoil at, say, Mach 0.6 or any other Mach number, but for now we'll try 0.6. All we have to do is go back into the configuration file and change the Mach number by editing the file with a text file from 0.8 to 0.6. Now, I would recommend copying your configuration file and making a backup, because if you screw it up and mess it up and it doesn't run, then of course you'll have to discover the bug. And so it's good to make backups and versions of your configuration files. So create your own naming system, create your own subdirectory system to keep track of your files. Create a README file or a little notes file describing what each subdirectory and case is. Because if you look at this a month later, you'll have forgotten what you've done. This is a good practice to get in. And so during office hours when you're talking to me and I ask you what a subdirectory is and you won't know and you don't have a recommendation file or a README file or some way to keep track of it, then that's a bad habit that you develop. So develop this good habit now. That's very important. So the first and only thing we really need to do is change the Mach number from 0.8 to 0.6. Let's do that in a configuration file. Let's edit the file and change the value. You'll look down, look in the file, you can search or scroll down and look for these lines. Mach underscore number equals 0.8. You notice some comments. The comment says Mach number, non-dimensional, based on free stream values. And so this Mach number is using the inlet velocity and ambient temperature to find the ambient speed of sound and taking u over c, and then solves for u based on m equals u over c. It's currently set to 0.8. Obviously, we should change the value to 0.6. Remember, percent signs are comments. Mach number does not have a percent sign in front of it. It's not a comment. This will change the incoming Mach number, of course, and it's enforcing the boundary condition. So the boundary condition is being enforced from Mach 0.8 to 0.6. So change that value to 0.6 and say, and your file should now read Mach number equals 0.6. See how that's 0.6? Easy. We can also change the angle of attack if we wish. So let's change the angle of attack from alpha 1.25 to 0. So go in the configuration file and find the lines that says angle of attack in degrees and change AOA to 0.0. Now, save and exit the file after you change Mach number to 0.6 and angle of attack from 1.25 to 0.0. Save and exit. And now you're ready to rerun your code. You don't need to do anything differently. Just type in SU2 CFD and the configuration file name and hit enter. Now you'll see that your code will overwrite the previous configuration files. So I recommend when you do this, creating a new directory, copying the configuration file, the grid file, and the symbolic link file into that new directory, and give it a new directory a name which is representative, and of course, execute the file. This way you'll have one subdirectory for Mach 0.8 at AOA 1.25 and a new directory and new solution files all in their own self-contained subdirectory of Mach 0.6 and angle of attack 0. Your code will run just like it did before, and you'll see output of the major columns. You'll see columns like this. The simulation run using a single driver. Anyway, you'll see iteration 0, 1, 2, etc. And all the information before will be the same except for the Mach number of angle attack. And here's your coefficient of lift and drag at initial iterations. Once again, you'll see these columns. And remember, each row represents an iteration as the solver is trying to converge to a numerical solution. The first column is iteration. This is the root mean square of the residual of density, which we want to drive to a very small zero value because it's the error in the solution. And here's the coefficient of lift and drag. So we want to see near the end of the solution when it converges. In this case, the solution converged to iteration 132, and we've reached a residual of negative 8.0192, which is less than negative 8, which was the same convergence criteria we had earlier. And now we have, of course, at this converged criteria, a converged solution. You see how CL and CD are not changing. Coefficient lift and drag. See they're labeled at the top of the columns. Of 0.000683, that's the coefficient lift and drag of 0.000225. So see how these are different than the higher Mach number and angle of attack case. Compare them now. So what does it mean if iteration 127, 130, and 132, etc. all have the same values as CL and CD? It means with increasing iteration count, the drag and lift are not really changing, but we are reducing the error in the solution. Ideally, we want the residual, this column, to go to a constant value of increasing iteration and the lift and drag to go to constants. That is what we want when we find a converged solution. And we want the the residual values of density and all other field variables, velocities, energies, etc. We should have residual columns, not just for density, but for every variable when we're doing this in practice to go to some very, very, very small value. The residual is the measure of the numerical error within the solution. That's why you want it to be very small. So now we found, with a simple rerun in the code with changing 2 lines in the configuration file, the angle of attack and Mach number, the new coefficient drag. You can experiment with this. Change the Mach number to any value you want, 0.2, 0.5, 1.5. See what happens. In some cases, your solver will crash. In some, it will, of course, converge. You can also be free to change the angle of attack. Change the angle of attack to like 45 degrees, negative 10 degrees, 0 degrees. Experiment, run a few cases, and you'll get used to seeing the results. For every case, visualize both the contours of pressures, Mach numbers, etc., and also look at line plots with, of course, coefficients and lift and drag. The more you try and experiment, the more you'll understand in the CFD code. And you will get stuck and you will have problems. That's why it's only important to change one thing at a time. Only change alpha. For every case, create a new subdirectory. Only change alpha, only change Mach number or other type or boundary condition in the code. Experiment. But only change one thing at a time. That way, when your code crashes and it doesn't work, you'll know exactly why. If you go in and change Mach number and angle of attack at the same time, and it crashes, you will not know if it was the Mach number or angle of attack which is causing the simulation to crash. And so using this iterative technique, you'll be able to isolate the errors in the solution. Next time, we're going to go back to the beginning and look at more in depth of the overall field of CFD. During this time, make sure that you have your solver running, your visualization software running, and your grid generation software running. Try this initial tutorial multiple times to get used to it and ingrain it in your mind. These are the most basic concepts of operating a CFD code, which is research-based, industrial-based, that there is. Now, commercial codes with fancy and beautiful graphical user interfaces are doing some of these steps for you automatically. But by learning to do them, you're finding out and learning the fundamentals. We're going to talk more about these fundamentals in the next class when we talk about different methods of investigation. So this is really the lecture part of the class and the academic part of the class we're moving into. We'll have homeworks, of course, which looks at the academic portion and numerical portion of the class, which will look at these in more depth. We'll talk about methods of investigation next class. There'll be experimental, theoretical, and CFD. There's 3 kinds. And contemporary modern research and development programs use all 3 seamlessly in an integrated team environment. In this class, we'll focus on CFD methodologies, on how they integrate with experimentalists and theoreticians, if you're lucky enough to work with an expert theoretician, that is. Then, of course, we'll look at the aerospace industry today and the contemporary use of CFD, and we'll go over in more depth the entire CFD process from problem definition all the way through pre-process, solver, post-process, and of course, how it's integrated with the CFD industry. Thank you very much for your time today. I'm Professor Steve Miller.